University of Illinois Extension.
Wednesday series, and I'm so happy that everyone has been able to join us. If you have missed one, or you want to rewatch one, or tell it to a friend to watch, these are all going to be available at the end of the month. All these recordings are going to be available at the end of the month on the Kankakee Valley Forest Preserve District on their webpage. So at the end of the month, you'll be able to catch up with all of the weeks that we have had, and we've had some fantastic presentations. And so I think you will want to re-listen to them and re-watch them again, or tell some of your friends too. So without anything else, I'll turn this over to Maria and we'll get started.
Hello, everyone. My name is Maria Niemerg, and my presentation, like Holly had said, is to be or not to be predicting insect distribution in Illinois specifically. So first, I'd like to talk about species biodiversity. According to some researchers, it is estimated that there are between 1 to 5 million species here on Earth, and primarily that includes, that estimate is primarily insects. Other researchers have estimated that between 2 and 5 million species remain undescribed, and that's about 70 to 90% of existing species might remain undescribed. This is concerning because some of the species are in decline. Since the rise of human civilization, it is estimated that about 83% of wild mammal biomass has been in decline, with a 60% decline in fish, amphibians, reptiles, mammals, and bird abundances from 1970 to about 2014. Because of this sharp decline in abundance, some have suggested that this is a potential mass extinction event. Insect researchers in particular have noticed a dramatic decline in insect range, taxonomic richness, and occurrence. And they have termed this trend and this time period as the insect apocalypse. Some of the reasons for species decline, the number one reason is habitat loss and degradation. If species don't have the right habitat, they struggle to adapt to their new environment, and sometimes it doesn't have the natural or the necessary habitat variables to thrive in that environment. A lot of natural areas have been converted to urban or agricultural lands. Waterways are also impeded, so this can include dams and channel straightening, or just channelization in general. The reason why that's very detrimental to species, like impeding waterways, is that it limits the amount of space that species can traverse in the watershed. So if a species needs to travel upstream, let's say, they'll be stopped by any sort of impediment. So if a dam is there, they can't traverse past that dam. Another reason for species decline is overexploitation through farming and such. Invasive species are also a very big problem. When an invasive species is introduced from its native land to a new area, oftentimes it doesn't have its natural predators. So instead of competing with its competitors to try to survive and having that homeostasis there, those invasive species don't really have to compete or aren't limited by their natural predators. Instead, they're competing with the native species who aren't adapted to those invasive species. Oftentimes, because the invasive species don't have the predators, they out-compete the native species, so they take a lot of the resources. Air and water pollution are also a big factor, and diseases. In Illinois, the landscape has changed dramatically. From 1820, about 22 million acres, it consisted of about 22 million acres of prairie and about 14 million acres of forests. by the 1900s, most of the prairies were converted into agricultural lands. And by 1978, it was thought that only about 2,300 acres of high quality prairie remained. For reference, that's less than 1% of the previous existing prairie area. So as I mentioned before, habitat loss is one of the greatest reasons for loss in biodiversity. So to promote biodiversity, we want to restore habitats. Larger areas that are closer together, larger natural areas are better. That just promotes more migration between different habitat patches. And again, more area leaves room for more species to thrive in that area. When we restore small patches, that can be okay, except that with small patches, you might have a lot of species that congregate there at first, but because of its limited size, we can lose some biodiversity. So that's what we refer to as a biodiversity sink, where we lose species. One of the major goals for park and natural area management is to restore habitats. Park managers will often ask themselves, what should the land be restored to? So what natural habitat features should be restored in that area? They might also like to know what species are likely to benefit from that restoration. And also what species are likely to occur near that restoration site or on site once it is restored. For example, for my project, I was working in the Starved Rock State Park. The managers there had acquired a large amount of land, and they wanted to know what the high quality areas of that new land was, and also what were the low quality areas. Now, the high quality areas they wanted to use for habitat restoration, specifically for species diversity, and for the lower quality areas, they wanted to do something more like with making trails and areas for people, such as picnic areas or restroom. They also wanted to know what species already occurred on site. Before they started to do anything, they wanted to know what was already there, and also what rare species might be present if they are not detected. One potential method for reaching this goal is to sample for every possible species on site. Now, for larger mammals, that could be reasonable, but for insects, that's not achievable. And a main reason is because insects are so species rich. As I described earlier, I mean, if we're looking at 1 to 5 million species predicted on Earth, I mean, and insects are a majority of that, that means that we would have to look for a lot of species and then identify all of them. That would be extremely time consuming and require a lot of specialized training to identify or capture and identify all of those insects. So a different method for reaching that goal is to create what's called a species distribution model. And that would be used to predict which species could occur on site. So species distribution models, also called SDMs, are a very common method for predicting species distribution. What they do is they take observation records and they pair that with the preferred environmental variables of that target species. So let's say if a species likes a certain temperature, then we can input that into the model and look for other areas that have the variables that that species prefers. One of the common tools is called MaxEnt. It uses presence-only data. So if there's a species there, that's the kind of data that we use. We put in the environmental predictors and define the landscape. And so what it does, it extracts a subsample of what we call background locations. So those are the locations where we're predicting that target species to be, but we don't actually know if that species is there. Again, it's a model, we're trying to predict it. Some of the main limitations to SDMs is that the number and the accuracy of observations. So SDMs require a large number of observations. I mean, we're pulling from a lot of different habitat variables, so we need as many points as possible. And that's not always feasible with rarer species because rare species are harder to find, so they'll have fewer observations. The accuracy of environmental data that are important to the target species is also a limiting factor because sometimes we do not know what the species actually prefers. Is temperature important? Likely yes, but we don't know. And other factors too. In many cases, especially for insects and rare species, we just don't know what they prefer and what's important to them. The modeling method is also a limitation because it is difficult to understand the inputs. So it takes a long time to learn how to use the software and also to create a good SDM. Because there's a high learning curve and it's difficult to understand, some researchers just use the default settings, and that means that they might come up with a model that is not as accurate when if they knew how to use, or if they knew all the inputs, they could come up with a better combination that would better reflect the prediction of that species. And also the way that we interpret the models can be difficult, so that's another limitation. For insects specifically, we're dealing with a large number of insect species. That is very time consuming. A single species distribution model takes a very long time to make and also get right. So to have a large number of species, it's not always feasible to do that with insects. A lot of times there's poor habitat preference information for insects. Also, they are much smaller, so some of their habitat preferences could be smaller scale compared to some of the larger mammals. As I said before, there are fewer records for rarer species. In my case for this project, some of the species on my list only have 1 or 2 records, and for a species distribution model, that's not enough. I will note that a lack of records does not mean that a species is not present. So for my model, I obtained records and then I created a convex hull polygon for each species. I'll get back to what a convex hull polygon is. I also don't need habitat specific data, so it's not restricted to trying to put the right variables into this model. It can be used with a limited number of records. In some cases, again, I only had 1 or 2 records, and that is enough to work with my model. It's appropriate for presence-only data, and it's good for a large number of species with very little known life history information. Some of my limitations for this model, however, is that it is sensitive to location errors. So because I'm not using habitat information, it's just doing a very broad estimate as to where species are. This can sometimes lead to overprediction and in some cases to underprediction. And we'll get into that once we look at the results. So the species that I decided to model are based off of the species of greatest conservation need list and watch list species. I have a total of 528 insect species, which sounds like a lot, but again, if we're going back to how many estimated species there are, it's not very much. Anyway, 44%, almost half of all of the insect species on this list are butterflies and moths. The other 32% are aquatic species such as caddisflies, dragonflies, mayflies, and stoneflies. 18% are true bugs. Now think stink bugs. I mean, you might find those in your home. And the other 5% are all the other insect groups, including beetles, bees, and wasps. That last 5% is very important in a sense because beetles tend to be one of the most species rich of all the insect groups. So I think there's only 1 or 2 species on my list. It's not very much. The International Union of Conservation for Nature's Red List of Threatened Species, what they do is they classify species and they give them a conservation status. For a lot of vertebrate, or about 42% of described vertebrates have an assessment. So they've been assessed for their conservation need versus only 0.3% of invertebrates. That's very concerning when we think about insect conservation, because that means we don't even know what the conservation status is for many of these species. That's, again, akin to thinking about the beetles. If we're only have a couple species, what about all the rest? We don't know exactly where they fall on the need for conservation. Okay, so for my model, I used 3 different data sets. The first one is from bugguide.net. Bugguide is dedicated to collecting observations of insects, spiders, and related critters in North America. What's really cool about this data set is that anyone can input records and then those can be verified by other users on the site. For my project, I have about 5,222 records. And as you can see, it's kind of, take note of the spread of observations on this map because it'll slowly increase with the data sets. As you can see here in my second data set, which is from the Illinois Natural History Survey, what's really cool about this data set is a lot of these records are museum quality records, meaning that they are very well preserved, and a lot of taxonomic experts are the ones who have inputted those records into the database. What's really cool about this is also that taxonomic experts tend to specialize in their target group. And so they are able to go to a place and look for species that tend to be rarer. They know what to look for. For my project, I have about 6,207 of these records. And finally, my third data set, it is from the Global Diversity Information Facility, or GBIF. The aim of this database is to provide anyone with records from across the globe. And as you can see, I mean, the whole database has about 2 billion records from over 92,000 databases. It's very impressive. As you can tell, there are a lot of records in my data set, so it's about over 75,000 records. In addition to the data sets, I was looking at 3 different scales. So I was looking at, what if I only took observations within Illinois? And then I increased that scale to look at Illinois and the surrounding states. And then finally, I looked at observations across the United States. So to make a predicted range, I use the convex hull method that I mentioned earlier. So what this method does is it takes a species and creates a polygon around the outermost observation records. On the left, you can see that one of the species is highlighted in light blue. And on the right, you can see how it had generated a polygon around all of the data points. And it used the outermost points as the border for that polygon. I did that for every single species at all the different ranges. This right here is one of the outputs. It's very, very busy because I had a lot of species to work with. On the right, you can clearly see the different edges of the polygons, and on the left, you can see how some of those what some of those polygons look like. So from there, I decided to make a heat map. One way to do that is to turn those polygons into what we call a raster, meaning that each polygon is divided into small pixels, and then I can add up those pixels. So for example, on this left picture, I have 3 different polygons, and on the right, it shows how many, what's the prediction of how many of these polygons or species occur in that pixel. The parameter I used is if the polygon overlaps with the center of the pixel. So the center would be the little black dot. If we look at the blue polygon on the left, you'll see that it overlaps with 3 of the pixels. So that would be on the second row, the 2 leftmost pixels on the second row, and then that third row, the second pixel. And that's reflected on the right. So we have a single species on the first two. So right here, can you guys see my mouse? Anyway, if you look, there
No, we
is
don't see your notes.
my mouse.
Yes, we can see your mouse.
Okay, so as you can see, these two overlap, and then this one. So we have one. Sorry. We have one, and then here we have an overlap of 3 of the polygons. So we have 3. So this was essentially how I made that heat map. So as you can see in the results, this is what I call the heat map for all the species at the Illinois scale. The lighter the color, the more species I predict at that location, at those locations. One thing that's very interesting is at the Illinois scale, there seems to be very few species on the edge, or what I will call the edge effect. This effect actually makes a lot of sense because if I'm taking observations only from the Illinois scale, so only in Illinois, I would need to have a lot of observations on the edge to not have that effect. Again, if I have only 3 observations on the very edge, then the polygon isn't going to overlap as much as it is in the center where a lot of the polygons can overlap with each other. Something else to note is, I mean, if we look at Bug Guide, we didn't have as many records in Illinois, and you can definitely see how that's reflected in the gradient of this of that prediction. There's also a lot of missing data, which is including, or a lot of areas with no data, which is represented by the blue. Now the Midwest scale is where things get a little bit better in terms of no edge effect. But there's a different trend that we can see here, and that is that it appears that Southern Illinois is less species rich than Northern Illinois. One of the potential reasons for that is because of the parameter I used for the Midwest scale. If you see here, Southern Illinois, there's only the buffer around Southern Illinois isn't very large compared to Northern Illinois, where we have all of Wisconsin and all of Michigan to work with. Missouri and Kentucky aren't that much in terms of a buffer, so there's not as much area for observations to be noted in Southern Illinois and past Southern Illinois versus, again, Wisconsin and in Michigan. Now for the US scale, I would expect to have a different kind of gradient because we don't have the edge effect as we saw in the Illinois scale, and we also don't necessarily have that limitation of no records, not as many records in Southern Illinois, but we still see a gradient towards the northeastern part of the state. I'm not exactly sure why that is the case. I can hypothesize that based on the records that I noted in the US scale, a lot of them tend towards larger cities and larger, more populated areas. So maybe it could do something with that. More people looking and recording near higher populated areas across the United States. So some things I would hypothesize about my predictions is that a smaller data set at a smaller scale will underpredict the actual species richness at the target site. If you remember the Bug Guide at Illinois, I mean, there was a lot of area that predicted no species, and I would think that's highly improbable that there aren't any of those species there in those areas. In contrast, I would think that the larger data set at the larger scale will overpredict the actual species richness. So if you think about it, if we have a species that has been reported in, let's say, California, or the West Coast and the East Coast, but not in the Midwest, if I'm looking at the United States scale, then it will say that it occurs in the Midwest, even if it might not. So instead of looking at just the Illinois scale or the US scale, I hypothesize that the Midwest scale might be the closest to the actual species richness at a site. If I look at the different data sources, Bug Guide alone doesn't seem to be as comprehensive. It seems to be lacking in observations, and I believe that that's dramatically under predicting the species. GBIF, on the other hand, might actually be enough to model future predictions. So if someone in a different state, let's say in Wisconsin, if they wanted to run a very similar model, then I think they could potentially just use GBIF's data instead of trying to pull from other data sources. Given that GBIF, again, has a lot of databases that they put together already, it already includes some data from Bug Guide and INHS. So I'm going to apply this to the bumblebee species. We're going to get a closer look at what that looks like if we're just looking at one group. Some background on bumblebees. So bumblebees are generalist species. One of the most important ecosystem services that they provide is called buzz pollination, and this helps pollinate tomatoes, peppers, and cranberries. Their life history is really interesting. So solitary queens will emerge from hibernation. They will look for a place to nest. So that means that if there is a crevice, they will likely try to nest there if it's suitable. Some of the suitable places that we found nests in are rodent burrows, for example. Another place that they could nest is in crevices near your home. Again, if they're opportunistic nesters, then they'll look for a suitable place to build a nest, and they will build a nest there. There have been reports by people in the state of Illinois who have found nests near their property, which is actually something that's pretty cool. Their nest size can be between 50 and 1,000 individuals, and that varies by species. So what the queen does after she builds her nest is she takes care of the first brood, and then once that first brood is able to forage, then she continues to lay eggs, and the workers then care for the rest of the brood. At the end of the season, the old queens will die, and the newly mated queens will be the ones to hibernate. Cuckoo bumblebees are really cool in that they don't have queens. They're social parasites, so what they end up doing is the females will emerge later than the bumblebee queens, meaning that the queens would have already had established nests. And what these females will do is they will lay their eggs in other bumblebee nests so that those workers will rear the cuckoo bees young. Historically, there have been records of 18 species occurring in Illinois, 3 of which are cuckoo bumblebees. For my project, I have 8 species listed on the species of greatest conservation need list. And these right here are the 8 that I'm focusing on. All of these pictures are obtained from the Bumblebee book, which I will show at the very end. I won't go through all of these species. I'll just have you take note of the different color patterns. This is something that's very important for a bumblebee identification because sometimes the difference between a species is whether the head is yellow or not. I will also like to put extra focus on that very first bumblebee on the upper left, the rusty patch bumblebee. That one is a very important bumblebee. Also, to note, especially when we get to the results, some of these bumblebees haven't been seen for a very long time. let's see. The tricolored bumblebee, for example, hasn't been seen, at least according to GBIF, hasn't been seen since 1929. And the yellow banded bumblebee hasn't been seen since 1960. And the variable cuckoo bee hasn't been seen in Illinois since 1986. Again, these are all according to GBIF, though some of those might have changed recently. So as I mentioned, the rusty patch bumblebee is a very important bee in that it's one of the first to emerge in the spring, one of the last to hibernate. Its nest size is about 1,000 individuals. It was once found in 28 states, and now it's only found in 9 states. It's declined 87% within the last 20 years. What makes it so important is it was one of the very first bumblebees to be listed as endangered, and that was in 2017. Some of the reasons for its decline, as well as decline in other bumblebee species, is disease, pesticide exposure, habitat loss, and climate change. So right here I have the number of observations for bumblebees specifically. As you can see, there's only a couple hundred for Bug Guide and INHS, and over 18,000 for GBIF. As you can see also in the map, earlier I was trying to describe that trend at the US scale. If you look at GBIF, you can see a lot of the records are congregated in that upper right-hand portion of the United States. So the trend could lean towards the northeastern part of the United States. Because I'm dealing with less species here, it does look more geometric, if you will. As you can see, Bug Guide doesn't really have very many, doesn't predict very many species. There were 3 species that occurred at that scale, and only 2 of them overlapped, so you have a maximum of 2. Versus INHS and GBIF that are predicting 6 and 7 of those 8 species. Again, we see there is a slight edge effect with the Illinois scale. And we also see a very similar effect with the less species rich southern portion of Illinois and more species rich northern portion at the Midwest scale. At the US scale, GBIF is recording or predicting that all 8 species can be found in Illinois. And as I've pointed out earlier, 3 of those species haven't been recorded since the mid-1900s, and they haven't been seen in a very long time. So that could be an example of potentially of overestimating the number of species. So one of the things I could do for future models is to pair those models with observations in sites across Illinois. So actually going and sampling 4 species across Illinois and trying to see how the species lists, how those tie into the models. A different way that I could model these species is instead of using states as the borders, I can just put a buffer around the target state. That could eliminate the trend we saw in the Midwestern states, because again, we had a lot of area coverage in the north and not as much in the south. So now I'm going to talk about insect conservation and how you can contribute to this. Cordoso et al. 2011 outlined 7 impediments to invertebrate conservation. The first one is that the public lacks knowledge of the beneficial services that invertebrates provide. In a lot of cases, when I talk to normal people, they don't really like bugs, and I totally understand it. Not a lot of people do, but they do provide a lot of beneficial services. And the more that I got to learn about insects, the more I could see them for the benefits that they provide instead of these little creepy crawling things that I would want to smush. Um, the second thing is that decision makers are unaware of conservation problems because we don't really know how imperiled some of the species are. When decision makers are trying to plan how they're going to use land, they don't always know what species are in need of conservation and which ones are not. Because as the third one points out, is that there's a scarcity of fundamental studies, so we don't really know what could be important. Many species are undescribed. Full species spatial ranges are unknown, so we don't really know exactly what the range of species are. The species abundance and the change in abundance over time is unknown. So we don't really know how the number of a particular species is changing. For example, for bumblebees, in the wintertime, that abundance, they don't seem to exist because they're hibernating. In the early springtime, their abundance would be low because the queens haven't established their nests. But in the heat of summer, their abundance definitely increases. And that's only looking at a yearly basis. Now, if we stretch that to over time, we can see just how many individual bumblebees of a certain species, how that changes. So like for the rusty patch bumblebee, we haven't seen as many individuals over time. So we can see that there's a decrease in their abundance. But a lot of species, we don't have that information. And the last thing is that there's a lot of unknown life history information and a response to habitat change. We don't know how certain species respond to changes in their habitats. So how can we conserve species that we don't know exist or species with very little life history information? The solution is exploration. Taxonomic entomologists, that's what they do in part. They specialize in identifying limited groups of insects. They actively go out and search for new species and ones previously known to science. This gives them an innate knowledge of key life history information. They can go out to a project site and they can intuitively know where to look based on habitat preferences with the species that they work with. They know what they can expect to find, what they expect to find based on those habitat features and the season in which they're looking. Sadly, a lot of taxonomic entomologists retire without being replaced. This is pretty detrimental because without them being replaced, we lose a lot of that critical life history knowledge and the skills needed to find new and rare species. This leads to a lot of species remaining undescribed. And also the species that exist, we lose a lot of the monitoring. So we don't know how, again, we don't know how the abundance changes over time. On the right, I have a series of pictures that of one method for sampling for insects, just to show the magnitude of what we're looking at. So I have a light trap that's set up, and insects are attracted to that light during the nighttime. And at the end of the night, we collect those and preserve them. And as you can see in the bottom right picture, that jar is filled with bugs, and they all need to be identified. So taxonomic entomologists, that's their job. They go through and identify the species that they're familiar with, and that takes a lot of skill and a lot of time to learn that skill. So there's absolutely a growing need for specialists and funding for them to go out and search for these important species and for other taxonomic research. So what happens if we don't have the specialists? That's where you come in. Your observations make a difference. The main cause of these conservation impediments is the lack of information. So with more people looking, we get more information about these species. Many species might be present, but no one is looking for them. Again, the lack of records does not mean the lack of species presence. For example, the northern amber bumblebee. There was a new record that I had found. I didn't find it, but I saw that someone had found the northern amber bumblebee in northern Illinois last year. And that's pretty huge because previously the last record of it was in 1954. So someone came across this bee and others identified it as the northern amber bumblebee, and that is a very good sign that maybe we can find other populations here in Illinois. So how do you go about, adding to this scientific database? One way to do that is to use iNaturalist. iNaturalist is an online social network of people sharing biodiversity information to help each other learn about nature. They're a crowdsourced species identification system. They're also an organism occurrence recording tool. What's really cool about this database is that they also have online projects with specific goals. So if you're interested in birds, let's say, you can go and look up if there are any projects where people are specifically looking for birds in a particular area. And you can add to those observations or to that project. So I'm going to go through how to add a record into their database using my phone. Here on the right is an observation I made of a bumblebee. Now, you can use photographs or you can do sound recordings. It depends on the species. Let's say for frogs, for example, if you were out at night, you could take a sound recording and input that into a database. Now, when taking pictures, especially of very fast and skittish species, something that what I like to do is I like to take a video of that species. So as I approach, if I know that there's a high chance that it'll fly away, I approach slowly and I take a video and I get as close as I can. And then later I can go back and screenshot the best pictures or the best frames that best reflect the identification characteristics that I would need. Another option, if video is not available, is to take numerous photos as you approach the creature. That will help assure that when it does fly away, you do have something to show for that observation. Okay, so here I'm going to input that bumblebee that I had found. So I'm going to click the bottom right button to add the record, and I'm going to choose image as the record type. Once I put the image in, it is going to auto-generate what it thinks it is. So it identified that it is a bumblebee. And some of the top suggestions for that is the two-spotted bumblebee. That one is what I assume it to be. So something that's really cool about this is that you can click on the species you think it is and then go through a series of photos that have already been put in to compare it to your photo. So once I have put the photo in and identified it, you don't have to identify it, but because I knew what it was, I was able to do that. After I put that information in, I also added location and date collected. Those two pieces of information are critical for future research. Again, we want to have location information so that we know, okay, where was this found? And also when was it found? Because that can give us seasonality information as well. So once I've added all the information, I can wait for others to verify that species. If I didn't know what it was, I could leave it blank, and someone else can identify it. In addition to that, I also had other information for that species. So I knew it was alive. I knew it was the actual organism itself. And I also knew that it was an adult male. So I put all that information in there. And then again, after that, I just wait for that record to be verified so that it can become research grade, meaning that it can be used for research purposes, such as what I'm doing. Other resources. So this bumblebee book I had mentioned earlier when I introduced the 8 species, it has a lot of other really important life history information about bumblebees, as well as different color patterns that they can have, because some of the species have multiple variations of the same color patterns. Something I didn't point out about taking pictures, for bumblebees, we want to really try to get the segment colors. So you can see here in this picture, I mean, they're looking at yellow and 2 orange and yellow and then black at the tip. So we want to make sure we can capture what color pattern is here on the segments. And also the head can be important because we can see sometimes it really is a difference between a yellow head versus not yellow head for 2 different species. Bee Spotter is also a really great resource. It's specific for bees found in Illinois, Indiana, Missouri, and Ohio, but they hope to expand to other states as well. It has a lot of quick guides to identification and links to other useful information. One of the guide examples is here on the bottom, but it goes through how to distinguish between other common bees. And it's also another place where you can put or deposit bumblebee observations. And finally, what I want to end with is bees aren't the only species to look for, obviously. We also need help with other species. And a really great way to do that is to look up BioBlitz and see if there are any places that are holding a BioBlitz in your area. So what this is people get together and they try to identify as many species as they can in a short amount of time in a very specific area. And this could be from plants to mammals to insects, all of the above. And it's a great way to connect with more people and who are also passionate about getting to know the areas that they live in and also the creatures that are found within that area. I'd like to thank the University of Illinois and all my field crew members. I'd also like to thank the Illinois Natural History Survey and specifically Jason Robinson, my advisor, Dr. Eric Larson and Dr. Christopher Diederich, committee members, Dr. Wendy Shelsky, my project lead, Terry Twendele for her help with the map making and other GIS support, and Dr. Tommy McElrath at the Insect Collections. I'd also like to give a special thanks to the Department of Natural Resources.
We're getting a couple of questions coming in. Is BioBlitz available nationwide?
I'm not actually sure. That's something that I know they have some in Illinois. It might be something they do through universities. But I'm not actually sure about that.
Yeah, I don't know either. I don't know either. How did you said a little bit, but how did you decide that this was that the Bumblebee project was something that you were very interested in?
I actually stumbled my way across insects in general. I started working for Jason back in 2018 as an undergrad, and I thought doing water quality samples and some bumblebee work sounded cool, and here I am being a bug nerd. So I guess it worked. It very much helped that Jason is very good at what he does.
I was just gonna say to you, he could make anybody into a bug nerd.
Absolutely. I mean, his passion for again, just going out in nature and looking at the random critters that are around him. It is very inspirational for sure.
And if you haven't been, if you haven't been exposed to Dr. Jason Robinson, he comes usually in the spring and the fall. We have him do a walk in the forest preserve, and he points out, of course, insects, but he also points out edibles and other things that we're seeing off the trail. So he's very, if you see him come across as doing a workshop, he's very much worth your time.
Absolutely.
Any other questions while we have Maria here? Otherwise, if you think of something later on today or tomorrow or next week, please let us know. Oh, here's one from Joseph. When you construct your model, do you use in-depth mathematical statistics or use a descriptive model?
So for my models, let's see, I don't use any specific mathematical statistics for it. It's all run through ArcGIS Pro, which is a map making tool. I'm sure that, so I don't specifically use this, but there is a way to use like Python, for example, to construct scripts with the models. It would be, I know that they have raster analysis tools, and that's something that I would be doing or trying to use to compare those different models. You know, how do those models actually compare to one another? But um, I haven't used them just yet.
Great.